Physicists once believed the universe was a perfectly ordered machine. If you knew the starting conditions, you could predict everything that followed. Every motion, every force, every outcome. But that confidence began to crumble the moment scientists looked deeper, far deeper, into the world hidden beneath atoms. At the smallest scales of existence, the universe behaves in ways that are not just unusual, but fundamentally incompatible with the logic that governs our everyday lives. It is a realm where particles refuse to choose a single state, where information leaps across vast distances instantly, where time seems to bend, and where reality itself appears unfinished until someone observes it. Today we explore the quantum realm, a world that defies intuition, challenges physics, and forces us to question the nature of existence. These are the 10 strangest phenomena in quantum physics, each one a crack in the surface of reality. In the world we experience, objects commit to a single state. A coin lands on heads or tails. A door is open or closed. A person is here or there. But in the quantum world, particles refuse to make such commitments. They exist in a state known as superposition, where multiple possibilities overlap simultaneously. An electron can spin in 2 opposite directions at once. A photon can travel along every possible path at the same time. A particle can occupy several locations simultaneously, as if it were smeared across space. This isn't a metaphor. It is a measurable, repeatable fact. Only when we observe the particle does the cloud of possibilities collapse into a single outcome. Until that moment, the particle is not one thing. It is many. Superposition forces us to confront a disturbing idea. The universe may not decide what is real until someone looks. If superposition is strange, entanglement is even stranger. When 2 particles become entangled, they form a single unified system, no matter how far apart they travel. Change one, and the other responds instantly, not quickly, instantly, even if they are separated by galaxies. Einstein despised this idea. He called it spooky action at a distance, convinced it violated the speed of light. But experiment after experiment proved him wrong. Entangled particles behave as if the space between them simply doesn't exist. They share information in a way that defies classical physics and challenges the structure of space-time itself. Entanglement suggests that the universe is not a collection of isolated objects, but a deeply interconnected whole. At the quantum level, separation is an illusion. In our everyday world, barriers are solid. If you throw a ball at a wall, it bounces back. But in the quantum world, particles sometimes pass straight through barriers they should not be able to cross. This is quantum tunneling. Imagine rolling a ball up a hill. If it doesn't have enough energy, it rolls back down. But a quantum particle doesn't follow that rule. It can appear on the other side of the hill without ever going over it. It simply materializes there, as if the barrier were nothing more than a suggestion. Quantum tunneling is not rare. It is essential to the universe. It allows nuclear fusion to occur inside stars. It enables the electronics in your phone and computer. It plays a role in chemical reactions and even in biological processes. Without tunneling, the sun would not shine, and life as we know it would not exist. In classical physics, observing something doesn't change it. You can watch a car without affecting its motion. You can measure a rock without altering its shape. But in quantum mechanics, observation is intrusive. It changes the system being observed. Particles behave like waves, spread out, probabilistic, undefined, until the moment we measure them. Then they snap into a definite state. The act of observing forces the universe to choose a single outcome from a sea of possibilities. This raises unsettling questions. Does consciousness play a role in shaping reality? Is measurement a physical interaction or something deeper? Does the universe remain in a state of uncertainty until something, or someone, looks? No one knows, and that mystery sits at the heart of quantum physics. If there is one experiment that reveals the madness of the quantum world, it is the double-slit experiment. When particles are fired at a barrier with 2 slits, they create an interference pattern on the other side, the signature of waves. This means each particle somehow goes through both slits at once. But when scientists try to observe which slit the particle actually uses, the interference pattern disappears. The particle behaves like a solid object, choosing one path instead of both. Observation changes the outcome. The experiment suggests that particles do not have definite properties until we measure them. Reality is not fixed. It is fluid, probabilistic, and dependent on the act of observation. We tend to imagine empty space as nothingness, a silent void. But in quantum physics, the vacuum is anything but empty. It is a restless sea of activity. Particles appear and vanish constantly. Energy fluctuates. Virtual particles pop into existence and disappear in fractions of a second. This constant churning is known as vacuum fluctuations. It means that even the emptiest regions of space are alive with invisible motion. The vacuum contains more energy than all the stars in the universe combined. It is the foundation of the quantum fields, the invisible structures that give rise to all particles. The vacuum is not nothing. It is the most active place in the universe. In everyday life, watching something doesn't freeze it in place. A watched pot eventually boils. A watched clock continues to tick. But in the quantum world, observation can literally stop time for a particle. If you measure a quantum system rapidly enough, you can prevent it from changing. A particle that would normally decay can be held in its current state indefinitely. This is known as the quantum Zeno effect, named after the ancient philosopher who argued that motion was an illusion. Quantum physics proved him right in a way he never could have imagined. The universe behaves differently when you pay attention to it. Light has always been mysterious. For centuries, scientists argued about whether it was a wave or a particle. The answer turned out to be both. Light behaves like a wave when you test for waves, and like a particle when you test for particles. It changes depending on how you look at it. Electrons behave the same way. So do atoms. So do molecules. The universe refuses to fit into the categories we create for it. Wave-particle duality is not a flaw in our understanding. It is a fundamental feature of reality. The quantum world adapts to the questions we ask. If the double-slit experiment is unsettling, delayed choice experiments are downright disturbing. In these experiments, scientists decide how to measure a particle only after it has already passed through the slits. And somehow, the particle behaves as if it knew the future decision. It retroactively changes its past behavior. This suggests that the universe does not have a fixed past. Instead, the past remains flexible until the moment we observe it. Time at the quantum level may not flow in a straight line. Cause and effect may not be as rigid as we believe. Reality may be rewriting itself in response to our choices. Teleportation exists, not for people or objects, but for information. Using entanglement, scientists can transfer the state of one particle to another instantly, across distance. Nothing physical travels, no signal moves, but the information appears on the other side. Quantum teleportation has been demonstrated between particles in laboratories, across cities, and even between Earth and orbiting satellites. It may become the foundation of future communication, encryption, and computing. The universe has shortcuts. We are only beginning to understand them. Quantum physics doesn't just challenge our understanding of reality. It challenges our understanding of understanding. It reveals a universe that is not solid, not fixed, not predictable. A universe built from probabilities, connections, and mysteries that defy logic. Particles that exist in many states at once. Objects that communicate instantly across space. Time that bends, space that flickers. Reality that waits for us to look before deciding what it is. The quantum world is not small. It is the foundation of everything, and the deeper we look, the more impossible it becomes. Maybe the universe isn't meant to make sense. Maybe it's meant to be explored.